Hey everybody, so we're gonna show in this video that the sum of k odd integers is odd if k is odd. So what does this mean? This means that if k is odd, then a sub 1 plus a sub 2 plus dot 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 all the way to a sub k is odd. So that's cool. So that means if k is odd, then k is equal to 2m plus 1, because this is an even number is 2 times m, and we're adding 1 to it, so we're making it an odd number, for m in the set of all integers. So this means the set of all integers. Whoa, that's crazy. Of all integers. And also, we can represent the fact that each term is odd by saying a sub I is equal to 2n sub I plus 1 for some n sub I in the set also of all real integers where I is equal to 1, 2, all the way to k. Let's make the k a little better. Okay, yeah, that's a little better. Okay, so not only are we showing that we have an odd number of integers, but we're also showing that each term is odd. So how are we going to start this? Well, we're going to say that the sum a sub 1 plus a sub 2 all the way to a sub k can be represented as a summation from I equals 1 to k equals 2m plus 1, just like we wrote up there. And what are we summing? We're summing a sub I. So that's pretty cool already. Now, since this is a summation, we're summing to 2m plus 1. So let's remove that last term, and we'll split it up into a summation from I equals 1 to 2m. We'll stop writing the k of a sub I, and we're going to take out that last term, plus a sub 2m plus 1, because this goes all the way to 2m, and then this goes to the 2m plus 1, which is the kth. This is the kth term. So now we can now invoke the fact that each one of these terms is odd. So we'll use this right here. So we'll say that this is equal to the summation from I equals 1 to 2m of 2n sub I plus 1 plus 2n sub 2m plus 1 plus 1. So for these two values, we just substituted that in. And since this is a summation, we can split this up into two summations. So we'll say something like the summation from I equals 1 to 2m of just 2n sub I plus the summation from I equals 1 to 2m of 1. Let's write the 1 right there like that. Plus 2n sub 2m plus 1 plus 1. I'll try to make my ones a little nicer for you guys. Okay. And now we can evaluate this out a little bit. We can evaluate this into just 2m because this is just a constant right here. So one of the rules that we learn about summations is that when we have just a 1 in front of it, this just sums up to whatever we're summing up to. So then we can say, and also here, since we have a 2 here, we can factor out a constant. That's another rule of summations. So we can just write 2 times the summation from I equals 1 of 2m of just n sub I plus 2m plus 2 times n sub 2m plus 1 plus 1. So we turn this term or this expression into this expression, and now each one of these terms has a 2 in front of it, so we can factor out the 2 there, and we're left with 2 times the summation from I equals 1 to 2m of n sub I plus m plus n sub 2m plus 1 plus 1. So this is really good, because if we can show that this is an integer, which we can call r, then we have 2 times an integer plus 1, which is odd, which means that this entire sum is equal to this, can be expressed in this form. Now the good thing is all these values, this n sub I, this m, and this n, and that m, they're all integers. So since the set of all integers are closed under addition, then r is an integer. And that's really good, because now we can say that therefore the sum of k odd integers where k is odd is of the form 2r plus 1, which is odd. And there you have it. We proved that the sum of k odd integers where k is odd is odd. So if you made it this far into the video, thank you. And some people were telling me that the audio wasn't that great. So I'm working on that. But yeah, thank you for watching. And this has been a little proof.